What is a photograph truly? Is it a memory, a frozen instant of laughter or sorrow, or is it a record, an objective piece of evidence? For most of us, it is both a fragile bridge between the feeling of a moment and the fact that it happened. But there is one photograph that transcends this simple definition. It is a picture not of a single moment, but of 10 billion years. It is a document not of human life, but of cosmic history. It is an image that fundamentally altered our sense of place, of scale, of significance. We call it the Hubble Deep Field. You have seen it, even if you do not know its name. It is one of the most iconic images ever produced by humanity. A tiny, dark, seemingly empty patch of sky in the constellation Ursa Major, no bigger than a grain of sand held at arm's length. For 10 consecutive days in the deep winter of 1995, the Hubble Space Telescope, our unblinking eye in the void, stared into this abyss. It was a tremendous gamble, a controversial use of one of the most precious scientific instruments ever built. Astronomers fought for every second of Hubble's time, and the director Robert Williams was using his discretionary allotment to point it at nothing. Absolutely nothing. A region of space meticulously chosen for its profound emptiness, devoid of bright stars, nebulae, or any nearby cosmic clutter. The goal was audacious, almost mystical, to see if anything was there in the darkest corners of the cosmos. To push Hubble to its absolute limits, allowing the faintest, most ancient photons of light to slowly, painstakingly build an image on its sensitive detectors. Each photon had traveled for an eternity. Some began their journey before our planet had even cooled. Some carried news from the universe's turbulent adolescence, a time when the very first galaxies were violently coalescing from primordial gas. For 240 hours, Hubble gathered these celestial ghosts. 342 separate exposures, stacked one on top of the other, meticulously cleaned and calibrated to reveal what lay hidden in the dark. When the final image was assembled and released to the world, it triggered a collective gasp of astonishment. The void was not empty. It was overflowing. The photograph was a breathtaking, jewel-studded tapestry woven with the light of over 3,000 galaxies. Each smudge, each pinprick, each spiral of incandescent light was an island universe, a city of billions of stars, each potentially with its own planets, its own stories. There were majestic, well-ordered spirals like our own Milky Way. There were chaotic, misshapen galaxies still reeling from ancient collisions. And in the deepest, reddest parts of the image were the faintest, most distant objects ever seen. Infant galaxies barely formed their light, having journeyed for over 12 billion years to reach us. The Hubble Deep Field was not a picture of space. It was a picture of time. It was a core sample drilled down through the very bedrock of cosmic history, revealing layer after layer of the universe's evolution. It told us that our universe was not just vast, but ancient and teeming with structure, a place of profound beauty and unimaginable scale. It became our definitive family portrait. For decades, this image has been scrutinized by thousands of scientists. Every pixel has been analyzed, every galaxy catalogued its distance, measured its composition, determined. It is a sacred text of modern cosmology, a cornerstone of our understanding of where everything came from. It represents the known, the catalogued, the impossibly distant but ultimately comprehensible universe. It is a static masterpiece, a window into a past so remote it might as well be frozen in amber. The galaxies within it are so far away that in the span of a human lifetime or even a millennium they do not move. They are fixed points of ancient light. But perfection, it seems, is an illusion. Even in this most perfect of cosmic portraits, there was a flaw, an anomaly, a whisper of something that did not belong. Deep within the raw data from those 342 exposures, something was amiss. A single pixel for a fleeting moment was not where it was supposed to be. Or rather, a tiny chain of pixels tracing an almost imperceptible path across the frame, a path that defied explanation. For years it was dismissed. An artifact, A cosmic ray striking the detector, a common nuisance in space-based astronomy. A momentary glitch in the camera's electronics. A statistical phantom born from the noise of the universe. It was a footnote in the data logs, an imperfection polished away in the public-facing versions of the image, a tiny scar on a masterpiece that no one ever thought to question, because the alternative was simply unthinkable. The alternative would violate the very premise of the photograph itself. The Hubble Deep Field is a portrait of the deep, immovable universe. Everything in it is supposed to be an anchor, a testament to permanence and immense distance. But this tiny, ghostly trace was not behaving like a galaxy 13 billion light-years away. It was behaving like something else, something moving. And in the context of the deep field movement on this scale meant one thing. It meant that it was close. Impossibly, shockingly close. It meant that while Hubble was capturing the birth of the cosmos, something had drifted right in front of the camera. It meant that this pristine window into the dawn of time had been photobombed. What could it be? An asteroid from our own solar system? Possible. The main asteroid belt is a busy place, but the trajectory didn't match. It didn't conform to the neat, predictable orbital plane where most of our system's rubble resides. Its path was strange, tilted an outlier, moving with a purpose that didn't seem to belong to our sun's family. This was not a familiar local object. This was a tourist, a wanderer, a traveler that had begun its journey not from the cold, dark regions beyond Neptune, but from a place much, much farther away. It was a visitor from another star. Imagine for a moment the sheer staggering improbability. The universe is defined by its emptiness. The distances between stars are so profound they are nearly impossible for the human mind to grasp. To send a probe to our nearest stellar neighbor, Proxima Centauri, would take our fastest spacecraft over 70,000 years. And yet from the blackness between these suns, something came. A piece of another solar system, a fragment of a world that orbits a different star, was ejected from its home by some ancient, violent gravitational dance. Perhaps it was a planet, thrown from its orbit by a larger sibling. Perhaps it was debris from a celestial collision that occurred when our own sun was just a protostellar cloud. We will never know its origin story. We only know its journey. For millions, perhaps billions of years it drifted. A lonely pilgrim sailing through the galactic night. A cosmic castaway of ice and rock tumbling silently through the interstellar void. Its surface, blasted by millennia of cosmic radiation, would be a dark, angry red. Its core, a frozen repository of materials from its alien birthplace. It was a message in a bottle thrown into the cosmic ocean with no intended recipient. Then, by pure, unadulterated chance, its silent, aimless trajectory brought it into our tiny corner of the Milky Way. It fell into our sun's gravitational well, a vast invisible net that snares wandering objects. As it began its plunge toward the inner solar system, the faint, distant warmth of our star began to stir it from its long slumber. Frozen gases, dormant for eons, began to sublimate from its surface, creating a faint, tenuous atmosphere, a ghostly coma. It was becoming a comet, an interstellar comet. And at the precise moment this cosmic phantom was streaking through our solar system, in late 1995, the Hubble Space Telescope was undertaking its most ambitious observation. It was pointed at that tiny, vacant patch of sky. For 10 days, as Hubble stared into the past, collecting photons from the edge of time, this visitor from another star sliced directly through its field of view. It was a scientific miracle disguised as a statistical anomaly. The ultimate cosmic coincidence. A transient event from our own backyard, captured by accident on a canvas meant to depict the eternal. For decades, the evidence of its passage lay buried dormant in the archives, a single thread of displaced pixels in a sea of cosmic data. The technology and the awareness to search for such things simply did not exist. We hadn't even confirmed the existence of interstellar objects yet. The very idea was relegated to the domain of science fiction. But the data held its secret, waiting patiently for a new generation of astronomers armed with more powerful computers and a revolutionary new understanding of the cosmos, waiting for someone to ask the right question. What if the flaw wasn't a flaw at all? What if the ghost in the machine was real? That ghost now has a name: 3I, Atlas, the third interstellar object ever to be officially identified by humanity. Its discovery decades after the fact is a story of incredible scientific detective work, of piecing together a puzzle scattered across time and data. It is a story that forces us to reevaluate our most treasured images of the universe. It tells us that these portraits of the cosmos are not static. They are alive. They are dynamic. They are single frames in a much, much larger motion picture, capturing not just the impossibly distant, but the fleetingly close. The revelation of 3I, Atlas, hiding in plain sight, transforms the Hubble Deep Field from a passive window into an active net, a net that by sheer chance caught one of the rarest fish in the cosmic sea. This is the story of that catch. It is the story of how we found a needle in a haystack the size of the universe, how a missing pixel became a messenger from another star, and how the most famous photograph of the distant past revealed a stunning secret about our present, fundamentally changing our understanding of the river of time and the lonely spaces between the stars. The evidence was there all along, a faint whisper against the roar of creation. The challenge was learning how to listen. How do you rewind the clock on a single observation? How do you prove that a few displaced points of light, logged 25 years ago, represent a visitor from another world? The search began not in the sky, but in the numbers. Buried deep within petabytes of archived data, a new kind of archaeology was about to begin, an excavation of light itself. What does it mean to discover a universe by looking at absolutely nothing at all? It feels like a paradox, a riddle whispered in the language of physics. In our quest for knowledge, we are trained to point our instruments at the brightest objects, the most dramatic events, the brilliant flare of a supernova, the majestic swirl of a nearby galaxy, the radiant nursery of a stellar nebula. We search for the signal in the noise. But in the mid-1990s, a handful of audacious astronomers proposed a revolutionary idea, an act of cosmic defiance that would forever alter our perception of the cosmos. They proposed pointing the most powerful telescope ever built by humanity at the quietest, darkest, most profoundly empty patch of sky they could find, and simply waiting. They gambled that the truest signal was not in the noise but in the silence itself, a silence that held the faint, time-worn echoes of creation. This was not a decision born of idle curiosity. It was a desperate quest for answers to the most fundamental questions of our existence. By the early 90s, cosmology was in a state of tantalizing frustration. We had the elegant framework of the Big Bang, a theory that told us the universe had a beginning, that it was expanding and cooling. We had Edwin Hubble's own monumental discovery that galaxies were rushing away from us, their light stretched and reddened by the very fabric of expanding space. We could even detect the faint residual afterglow of creation itself, the cosmic microwave background radiation, a baby picture of the universe at a mere 3,800,000 years old. But between that primordial fire and the magnificent mature galaxies we see around us today, like our own Milky Way, lay a vast dark chasm in our understanding. A cosmic dark age. How did the universe make the leap from a smooth, uniform soup of hot gas to the lumpy, glittering, structured reality we inhabit? When did the very first stars ignite? How did those first sparks of light assemble themselves into the grand, galactic cities that now populate the cosmos? We had theories, elegant equations, scribbled on blackboards, and sophisticated computer simulations that painted ghostly pictures of what might have been. What we lacked was the definitive proof. We lacked a photograph from that forgotten epoch. We needed to see it with our own eyes. To do that, you need more than a telescope. You need a time machine. And floating in the silent vacuum 340 miles above the Earth, we had one. The Hubble Space Telescope, a marvel of engineering and human ambition, was our eye on the universe. Its journey had been fraught with peril. Launched in 1990 to immense fanfare, its discovery of a minuscule flaw in its primary mirror, an error barely the width of a human hair, turned a dream into a national embarrassment. It was a magnificent instrument rendered myopic, its vision blurred. But in a daring 1993 servicing mission, astronauts performed a breathtaking act of celestial surgery, fitting the telescope with corrective optics. The result was a miracle. Suddenly, the universe snapped into focus with a clarity that brought astronomers to tears. Hubble was reborn, its potential finally unleashed. It was this redeemed, newly powerful instrument that offered the first real chance to bridge that gap in cosmic history. All it needed was a target and a leader with the courage to point it there. That leader was Robert Williams, the then director of the Space Telescope Science Institute. The director held a unique power control over a small but precious portion of Hubble's observing schedule, known as director's discretionary time. This time was a resource more valuable than gold to the astronomical community, typically awarded to follow up on unexpected discoveries or to test bold new ideas that might be too risky for the conventional peer review process. Williams was about to make the riskiest bet in the history of astronomy. He proposed to dedicate a huge portion of his discretionary time, over 100 hours spread across 10 consecutive days, to a single monumental observation. He wanted to conduct the longest, deepest stare into the universe ever attempted. He wanted to drill a core sample through cosmic time all the way back to the dawn of galaxies. The proposal was met with fierce opposition from many within the scientific community. It was seen as an unconscionable waste of an invaluable asset. What if they saw nothing? What if after 10 days of staring into the void, the result was just a deeper void? The political and scientific fallout would be catastrophic. It would be a public failure for an agency, NASA, and an instrument, Hubble, that had only just recovered from its initial stumble. The telescope's time was meticulously planned years in advance, with countless teams of astronomers vying for even a few hours to unravel their own celestial mysteries. Williams was proposing to monopolize the instrument for a single observation, with an uncertain outcome, effectively shutting out dozens of other worthy scientific projects. He was in essence betting his career and a significant portion of Hubble's scientific legacy on a single roll of the cosmic dice. But he and a small team of supporters were convinced that the potential reward outweighed the immense risk. They believed that hidden in that profound darkness were the faint, ghostly signatures of the universe's first children. The first step was to find the perfect window. The location had to be chosen with surgical precision. It couldn't be just any patch of blackness. To see the faintest, most distant objects, the view had to be utterly pristine, uncontaminated by the light of anything nearby. The team scoured star charts, searching for a celestial desert. The target had to be far away from the bright, cluttered plane of our own Milky Way galaxy, whose thick bands of dust and gas would act like a cosmic fog, obscuring the ancient light they sought. It had to be devoid of any bright nearby stars, whose brilliant glare would wash out the unimaginably faint targets. It also needed to be in a part of the sky that Hubble could continuously view for a long period without being blocked by the Earth or the Moon, a so-called continuous viewing zone. After an exhaustive search, they settled on a minuscule patch of sky in the constellation Ursa Major, the Great Bear. It was a region of sky so unremarkable, so utterly devoid of interest, that it was almost never studied. To the naked eye, and even to most ground-based telescopes, it was a perfect, unblemished square of night. The area they selected was infinitesimally small, equivalent to the size of a grain of sand held at arm's length. Into this cosmic keyhole they would pour all the power and patience of Hubble. The instrument at the heart of this endeavor was the Wide Field and Planetary Camera 2, or WFPC-2. This was the very camera installed during the 1993 servicing mission, the device that gave Hubble its sharp new eyes. Its detector, a mosaic of 4 sensitive CCD chips, had a peculiar stair-step shape that would give the final image its iconic form. But this was more than just a camera. It was a sophisticated scientific instrument designed to dissect light itself. The plan was not to take one single long exposure. That would be impossible. The detector would be saturated with noise and peppered with the constant rain of cosmic rays, high-energy particles zipping through space that strike the detector and create false bright spots. Instead, the observation would be a meticulously choreographed symphony of hundreds of individual exposures. Over 10 days from December 18th to 28th, 1995, Hubble held its gaze, its internal gyroscope spinning silently, acting as a gravitational anchor to keep it locked on that single point with unwavering accuracy. As the Earth spun below, and Hubble orbited it every 96 minutes, the telescope's complex systems worked in perfect harmony to keep that tiny patch of nothingness centered in its view. For each short exposure, a filter wheel inside the camera would click into place. One filter would let through only deep blue light, another only green, another red, and another invisible infrared light. This process was critical. By capturing the same scene in different colors, astronomers could learn far more than what a simple black and white image could reveal. The color of a distant galaxy is a direct clue to its nature and, most importantly, its distance. Because the universe is expanding, the light from a faraway galaxy is stretched as it travels across billions of years of space-time. Blue light is stretched to green, green to red, and red into the infrared. This phenomenon, known as redshift, is the cosmic yardstick. By measuring how red a galaxy appeared across the different filters, the team could calculate its distance, and therefore how far back in time they were looking. Each click of the filter wheel was another step deeper into the past. In total, 342 separate images were taken. The raw data began to stream down to Earth, not as a beautiful picture, but as a flood of digital information, ones and zeros, transmitted to the Goddard Space Flight Center in Maryland. There, a team of scientists waited their anticipation, mixed with a profound sense of anxiety. Had their great gamble paid off, the process of turning that raw data into a single image was a monumental task in itself. For weeks, the team worked tirelessly. They had to write complex computer programs to meticulously align all 342 frames, layering them one on top of the other with sub-pixel accuracy. They had to painstakingly identify and remove the thousands of bright streaks and spots left by cosmic ray impacts, cleaning the digital canvas of these unwanted blemishes. They had to correct for the unique geometry of the WFPC-2 camera, stitching the 4 separate chip images into a single coherent mosaic. Slowly, painstakingly, as one layer of data was added to the next, a picture began to emerge from the digital noise. The darkness began to resolve itself. The silence began to speak. What appeared on their screens was not the empty void they had feared. It was the opposite of empty. It was a revelation. It was the universe. The image that materialized was one of the most important in the history of science. It was a cosmic jewel box overflowing with light. Where there had appeared to be nothing, there were galaxies. Not a few, not dozens, but thousands. Nearly 3,000 individual galaxies were packed into that tiny sliver of sky. Each one a swirling city of billions or even hundreds of billions of stars. Each one a potential home to countless worlds. And they were a bewildering motley crew. There were some elegant, familiar spiral galaxies like our own, and massive golden elliptical galaxies. But there were also strange, distorted, chaotic shapes, what astronomers called cosmic train wrecks. These were smaller, misshapen fragments galaxies, in the violent process of colliding and merging, their structures torn apart by gravity. This was not the orderly, mature universe we see in our own cosmic neighborhood. This was a younger universe, a wilder and more turbulent place. It was the era of galaxy formation caught in the act. They had found precisely what they were looking for. The colors in the final portrait told the story of time. The larger, whiter and yellower galaxies were closer to us, their light having traveled for a few billion years, but scattered among them were smaller, fainter, and intensely red smudges. These were the true prizes. These were the most distant galaxies ever seen, their light having journeyed across more than 12 billion years of space-time to reach Hubble's mirror. We were seeing them as they were when the universe was less than a tenth of its current age, a mere toddler in cosmic terms. The Hubble Deep Field, as it was named, was a direct photograph of our own cosmic history. It was a core sample drilled through time, with layers of younger galaxies sitting on top of older, more primitive ones, all the way down to the bedrock of cosmic dawn. It proved beyond any doubt that the universe has evolved. It was not static or eternal, but has a story, a narrative of birth and growth, of chaos and creation. The image became an instant icon, a window onto a previously invisible reality, fundamentally reshaping our understanding of our place in the cosmos. For decades that followed, this image, along with subsequent even deeper fields, was treated as a sacred text of cosmology. It was a perfect, immutable record of the distant past, a celestial fossil captured in a flash of ancient light. Every single point of light within its frame was meticulously studied, catalogued, and analyzed by astronomers around the world. Each smudge was a galaxy, an island universe, fixed at an immense distance, its position in the sky and in time locked in place by the laws of physics. The Hubble Deep Field was seen as the ultimate static tableau, a snapshot of a moment in cosmic infancy frozen forever. It was the definitive portrait of the ancient, unchanging heavens. But what if that assumption, the very foundation upon which our interpretation of the image was built, was flawed? What if one of those faint, insignificant points of light wasn't a distant galaxy at all? What if something in this perfect, static masterpiece of cosmic history had moved? What if a single pixel in this photograph, from the dawn of time, was hiding a secret much, much closer to home? But the key to unlocking that stubborn, 2-decade-old enigma would not be found by staring deeper into the void of the past. It wasn't another algorithm, another round of painstaking image processing, or a new theory of cosmic rays that would finally illuminate the truth behind that single anomalous pixel. The answer, incredibly, was not hiding in the digital archives of 1995. It was hurtling toward us through the solar system, a ghost from the interstellar dark, arriving with a story it didn't even know it was carrying. The clue was alive, and it was fast approaching. To find it, we must leave the silent contemplation of a single photograph and leap forward in time to a world of constant, vigilant surveillance. By the late 2010 seconds, our watch over the heavens had transformed. The solitary, patient gaze of a single great observatory had been joined by a global network of robotic eyes, sleepless and relentless. Among the most crucial of these sentinels is the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a pair of telescopes in Hawaii and Chile designed with a beautifully simple, if sobering, mandate to scan the entire observable sky every few nights, searching for anything that moves. Its primary mission is planetary defense, to find the city killers, the rogue asteroids on a collision course with Earth, giving us precious time to react. But in its tireless sweep of the cosmos, ATLAS sees everything. It is a vast, automated net dragged through the celestial ocean, and on the 28th of December 2019, it caught something extraordinary. It began not with a thunderous announcement, but with a quiet flag in a server room. A stream of digital information impossibly vast flowed from the telescope's camera into powerful computers, where sophisticated software performed a cosmic dance of comparison. The program took the fresh image of a patch of sky and meticulously subtracted an older image of the exact same patch. Anything that remained, any stray photon, any pinprick of light that wasn't there before was a candidate for discovery. Most of these fleeting apparitions are mundane, the glint of a known satellite, the gentle drift of a catalogued asteroid, or even the brief violent death of a distant star. The software is trained to filter this noise, to search for a specific signature, a faint, persistent smudge moving with purpose against the static backdrop of stars. On that December night, the algorithm registered just such an object. It was a barely there smear of light, an almost negligible collection of photons in the constellation Ursa Major. To the uninitiated, it would have been nothing, a flaw in the lens, a cosmic dust bunny. The system assigned it a provisional designation, A10E6 by 5, and as it did for hundreds of other potential discoveries that night, it automatically forwarded the coordinates and initial observations to the Minor Planet Center, world's clearinghouse for all things that drift and wander through our solar system. There it joined a queue, a list of celestial suspects waiting for confirmation for a verdict on whether they were truly something new or just another false alarm. This is where the human element re-enters the story of discovery. An astronomer on duty, likely sipping coffee thousands of miles away from the robotic telescope, would have seen the alert. Their first step is always one of skepticism. They would have cross-referenced the position with catalogues of known objects. Was it simply a poorly identified main belt asteroid, a periodic comet making its scheduled return from the cold outer reaches? The databases returned nothing. This faint smudge had no history, no known identity. The next step was a call to arms, a quiet digital one. A notice was sent out across the global network of observatories, both professional and amateur. "We have a candidate," the message essentially said. "It's here. Can anyone else see it?" And they could. Within hours, other telescopes began to pivot. In Arizona, in Spain, in observatories across the planet, astronomers trained their instruments on the designated coordinates. They too saw the faint, ghostly glow. Each new observation was another data point, another breadcrumb on this object's mysterious trail. These weren't just pretty pictures. They were acts of meticulous science, a discipline known as astrometry. Each image provided a precise measurement of the object's position, its right ascension and declination, at a specific recorded moment in time. With the first observation, you have a dot. With a second, you have a line, a direction of travel. But with a third and a fourth and a fifth, you begin to reveal the true magic of celestial mechanics. You begin to unveil the curve of its path. You can almost feel the intellectual tension building in those first few days. Astronomers around the world fed their precious data points into powerful orbital mechanics software. The initial plots would have been tentative, the projected path a wide cone of uncertainty. But as more observations poured in from across the nights that followed, that cone began to shrink. The arc became sharper, more defined. They were mapping its destiny, calculating its journey through our solar system. They could see it was falling toward the sun, its path a graceful, sweeping curve, governed by the immutable laws of gravity first laid down by Kepler and Newton centuries ago. For a time, it looked like a classic long-period comet, a visitor from the Oort cloud, that vast theoretical sphere of icy bodies encasing our solar system. Such comets travel on enormous stretched-out ellipses, taking thousands or even millions of years to complete a single trip around the sunday. They are members of our solar family, just the most distant and reclusive relatives. But something about this object's trajectory felt wrong. It was moving too fast. Comets from the Oort cloud arrive with a certain cosmic languor, having spent eons at the edge of the sun's gravitational influence. They are essentially falling from a near standstill. This object, however, seemed to have arrived with a running start. It possessed an intrinsic furious velocity, that couldn't be explained by the sun's pull alone. The numbers being crunched in computers worldwide were beginning to point toward a conclusion that was both scientifically thrilling and deeply profound. The key lay in a single crucial parameter of any orbit: its eccentricity. Think of an orbit's eccentricity as a measure of its shape. A perfect circle has an eccentricity of 0. The gentle ellipses of the planets in our solar system have eccentricities just above 0. As an orbit becomes more stretched, more elongated, its eccentricity approaches 1. Halley's Comet, for instance, has an eccentricity of about 0.967, a very long and skinny ellipse. An orbit with an eccentricity of exactly 1 is called a parabola. This is the escape velocity orbit. An object on a parabolic path has just enough energy to escape the sun's gravity, but only barely. It would coast away, slowing forever, never to return, but forever bound to the memory of its encounter. It is the line between being a prisoner and being free. As the data for A10E6x5 solidified, the number that emerged on computer screens sent a shockwave through the astronomical community. The eccentricity wasn't 0.8. It wasn't 0.97. It wasn't even a perfect one. The calculated value was hovering around 3. 3. A number that in the language of orbital mechanics is an unambiguous declaration of independence. An eccentricity greater than 1 defines a hyperbola. This is not the path of a captive. It is not the trajectory of an object weakly bound to our star. A hyperbolic path is a cosmic flyby. It is the trajectory of a wanderer, an interstellar interloper, a body that has entered our solar system from the vast cold emptiness between the stars and is destined to return to it. It was a one-way ticket. This was the moment of revelation. This faint smudge was not ours. It was a visitor from another solar system. The discovery was confirmed and announced to the world. A 10E6x5 was given its official historic name, 3I, Atlas. The I stands for Interstellar, a designation of profound significance. It was only the third such object ever definitively identified in human history, following the bizarre cigar-shaped asteroid Oumuamua in 2017, and the more conventional-looking comet 2I, Borisov, which had been spotted just months earlier. Suddenly, humanity was living in a new era. We were no longer just observing the traffic within our own cosmic neighborhood. We were beginning to witness the messengers from others. The discovery ignited a firestorm of activity. This was more than just a celestial curiosity. It was a physical piece of another star system delivered to our doorstep. What secrets did it hold? What story could it tell of its birthplace? The world's greatest telescopes were immediately commandeered. The race was on. 3I. Atlas was already past its closest approach to the Sun, a point known as perihelion, and was now heading back out, destined to fade into obscurity forever. Every photon was precious. Every hour of observation was a chance to read a page from a book written in a different corner of the galaxy. Spectroscopy became the tool of choice. By capturing the faint light from the comet's growing coma, the fuzzy atmosphere of gas and dust sublimating from its icy nucleus and passing it through a prism, astronomers could shatter that light into its constituent colors, a rainbow. Barcode of chemistry. The spectral lines revealed the familiar signatures of cyanide, of diatomic carbon and water ice, the building blocks of comets in our own solar system. But the true prize lay in the details, in the isotopic ratios. Were the atoms in its water the same heavy hydrogen variants as our own? Was the mix of noble gases locked in its ices comparable to the primordial cloud that formed our sun? These are the subtle dialects of cosmic chemistry, the accents that can betray an object's true home. Observing 3I, Atlas, was an exercise in cosmic archaeology on a deadline. The object itself was a time capsule, likely formed in the swirling protoplanetary disk of a completely different star billions of years ago. It would have orbited its own sun for a time before some chaotic gravitational encounter, perhaps a jostling of giant planets or the close pass of a sibling star, ejected it violently from its home. This cosmic orphan was then cast out, tumbling through the silent, near-absolute zero of interstellar space for an unimaginable length of time. Millions, perhaps hundreds of millions of years, it sailed the galactic currents, a tiny frozen relic of a solar system we will never see. Its journey was one of profound isolation, a silent pilgrimage through the dark. Then, by sheer dumb luck, its random walk through the galaxy intersected with the path of our own solar system. It fell into our sun's gravitational well, was briefly illuminated and warmed by a star that was not its own, and then slung back out into the eternal night. We were the brief, startled witnesses to one fleeting moment in its epic multi-million-year journey. The data collected during its short passage was frantic and intense. We saw it brighten unexpectedly, suggesting outbursts of volatile gases as fresh ice was exposed to sunlight for the first time in eons. We measured the reddish, complex organic molecules in its dust, hinting at a chemistry that was both familiar and subtly alien. We confirmed it was a comet, in every sense we understood, but a comet with a backstory that dwarfed that of any object born in our own celestial backyard. It was a ghostly traveler, a messenger, carrying the primordial recipe of its formation, untainted by the long history of our own solar system's evolution. As it sped away from the sun, its path was mapped with astonishing precision. Using the combined observational data from dozens of observatories over several months, astronomers plotted its hyperbolic trajectory with near-perfect confidence. We knew the exact angle of its arrival, its blistering velocity relative to our sun, and the precise vector of its departure. Its state vector, its position, and velocity at any given time was logged into our databases, a permanent record of its transient visit. Its story, as far as the scientists of 2019 and 2020 were concerned, was largely complete. 3I, Atlas, was a solved puzzle, a spectacular but understood phenomenon. It was a confirmed interstellar comet, a thrilling data point in our growing understanding of the galaxy, now receding from us at over 100,000 miles per hour, its brief, fiery encounter with our star already becoming a memory. The file on 3I, Atlas, was for all intents and purposes closed. The world's astronomers moved on to the next discovery, the next mystery. They had no reason to believe this object had any more secrets to give up. They had tracked it, they had characterized it, and they had bid it farewell. They could not possibly have known that the most important clue 3I Atlas had to offer wasn't in the light it was emitting now, but in the shadow it had cast years before it was ever discovered. Its neatly calculated trajectory, a testament to modern science, held one final, unbelievable revelation. For if you could trace that perfect hyperbola, not forward into the future but backward into the past, it would lead you on an unerring path to a very specific place at a very specific time. A collision course, not with a planet, but with a piece of history. And so, the trajectory was known. An elegant, hyperbolic arc, a path of impossible speed, was now plotted with chilling precision, not just into the future, but deep into the past. We had followed the phantom of 3I, Atlas, backward through the celestial clockwork, past its swing around our sun, beyond the orbit of Jupiter, beyond Saturn's silent rings, and out into the cold, empty spaces where our solar system's influence wanes to nothing. The computer models, running for weeks on end, had spun time in reverse, calculating every gravitational nudge, every subtle perturbation from planets it had never met. They produced a ghost of a path, an echo of a journey, pointing to a specific coordinate in the sky at a specific moment in our own history. December 1995. For most of us, the date is a faint memory. For astronomy, it is immortal. It was the moment humanity first stared into the abyss, and saw it staring back, filled not with darkness but with light. The Hubble Deep Field. The coordinates matched. The unthinkable, audacious, almost heretical idea began to form, not in a grand pronouncement, but in the quiet hum of a university server room and the hushed conversations of a few determined astronomers. What if? What if our interstellar visitor, this transient messenger from another star, had photobombed the single most important picture ever taken? The suggestion was met with skepticism, and for good reason. You were proposing to find a ghost in a cathedral. The Hubble Deep Field was a monument to permanence, a 10-day stare into the void designed to capture the faintest, most ancient and most stationary objects in creation. It was the very definition of a static image, a cosmic core sample drilled through space-time. In contrast, 3I, Atlas, was a phantom, a blur of motion. To look for one inside the other felt like searching for a specific raindrop in a photograph of the ocean. The challenge was monumental, a task of digital archaeology on an almost unprecedented scale. You cannot simply download the Hubble Deep Field from the internet and zoom in. The iconic image we all know is a final processed masterpiece, a careful collage of 342 separate exposures, meticulously stitched together, cleaned of cosmic ray strikes and balanced for color. The raw data, the actual photons collected by Hubble's Wide Field and Planetary Camera 2, was a sprawling, chaotic archive. It was a beast of old data, stored in archaic file formats on magnetic tapes that had to be physically retrieved from deep storage. This wasn't a search, it was an excavation. The team, a small, dedicated unit of data sleuths and astrophysicists, were essentially time travelers, attempting to rebuild a crime scene a quarter of a century old. Their suspect was a moving target, impossibly faint, and their evidence was buried under layers of digital noise and processing artifacts. Their first task was to refine the path. They couldn't search the entire field of view, that would be computationally impossible. They needed to know down to a fraction of a single pixel exactly where 3I, Atlas, should have been in each of those 342 frames. This required a level of astrometric precision that bordered on clairvoyance. They built a dynamic model of the solar system as it was in 1995, a perfect gravitational map. They then flew their digital ghost 3I, Atlas, through this simulation backward. The Sun pulled on it. Jupiter, a faint but insistent gravitational anchor, tugged at its trajectory. Even the tiny pull of Earth itself had to be accounted for. The result was a celestial thread, a predicted pathway of pixels arcing across the 4 separate detector chips of the camera. It was a corridor through space-time just a few pixels wide. If their visitor was anywhere, it was here. Now, the hunt could truly begin. They loaded the raw exposures one by one, and what they saw was chaos. Imagine looking at a black and white photograph taken on grainy film during a snowstorm and being asked to find a single specific snowflake that fell 25 years ago. Each frame was littered with imperfections. There were brilliant streaks left by high-energy cosmic rays, particles from distant supernovae that had slammed into Hubble's detector at near light speed, overloading the electronics. There were hot pixels permanently stuck on white. There were dead pixels eternally black. And beneath it all was the fundamental quantum noise of the universe, a faint, simmering static that washed over everything. The galaxies themselves, the very things Hubble was meant to see, were just faint, fuzzy smudges. And somewhere in this digital blizzard, they hoped to find a smudge that was even fainter, and that was moving. Weeks turned into months. They developed algorithms to automatically flag any potential candidate along the predicted path. The computers churned, spitting out thousands of false positives. A cosmic ray would strike right on the path, raising hopes for a few frantic hours before analysis revealed its telltale sharp edges and impossibly high energy signature. A cluster of noisy pixels would momentarily mimic a faint object, only to disappear under closer scrutiny. The team rode a nauseating wave of hope and disappointment. They were chasing a whisper in a hurricane. The original Hubble team legends in the field had spent months cleaning this very data to produce their masterpiece. What arrogance to think they had missed something, that a grain of sand had slipped through the finest scientific sieve ever constructed. The thought that this was all a grand exercise in confirmation bias, a beautiful theory slain by an ugly reality, began to loom large. The ghost, it seemed, was going to remain a ghost. The breakthrough came not from finding something new, but from inventing a new way to look at the old. Frustrated by the noise, one of the younger team members, a specialist in image processing, suggested a radical approach. Instead of looking for the object in each individual frame, what if they could make the frames themselves reveal the object? The technique was called temporal differential astrometry, a complex name for a beautifully simple idea. You take two images of the same patch of sky taken at different times. You perfectly align them, star for star, galaxy for galaxy, and then you subtract one from the other. Everything that is permanent, everything that is a fixture of the cosmos, the distant galaxies, the foreground stars, even the instrument's own flaws, disappears. It is cancelled out, becoming zero. The only thing that remains is what has changed, what has moved. It was a technique used to find asteroids in our own solar system, but applying it to the hallowed data of the deep field, with its mind-boggling faintness and ancient date, was a leap of faith. They selected two exposures of the same region, taken about an hour apart. These were images filtered to capture red light, where a distant icy body like 3I, Atlas, would likely be brightest. The software Word. It painstakingly mapped the faint lattice of primordial galaxies in the first frame, locking onto their positions. Then it did the same for the second. It stretched and warped the images with sub-pixel accuracy, ensuring a perfect alignment. Then came the moment of truth. The command was given: subtract. On the screen, the universe vanished. The thousands of galaxies, each a city of 100 billion stars, dissolved into a uniform neutral gray. The noise, the cosmic rays, the detector flaws, they all faded away. It was a screen of profound, beautiful nothingness. And then they saw it. It wasn't dramatic. It wasn't a flash of light. It was just a presence. In the first frame, a tiny cluster of pixels, no more than 3 or 4, glowed with a faint, ethereal white. This was a positive residual. Something was there. In the exact same spot on the second frame, an identical cluster of pixels was rendered in a deep, stark black. A negative residual. Something had been there and was now gone. They cross-referenced the coordinates with the trajectory model. It was a perfect match. A direct hit, right on the ghost's predicted path. The room fell silent. No one breathed. It was the digital equivalent of a single footprint on a barren shore. It was the first hint of evidence, impossibly faint but undeniably present. It was a whisper that had survived a quarter-century of silence. This was the key. This was the Rosetta Stone. They now knew its signature, its ghostly calling card. It appeared as a faint positive, then vanished. Now they could hunt for it with purpose. They abandoned the automated search and began a painstaking manual examination of all 342 exposures. It was a colossal, mind-numbing task, but it was now fueled by the fire of imminent discovery. They knew the object would be visible in some filters, but not others. They knew its predicted rate of travel across the detector. And with this new knowledge, they began to connect the dots. They found it again in an image taken 2 days later. A faint smudge, just a handful of photons, barely distinguishable from the background noise, but in a slightly different position. A position that perfectly matched the calculated orbit. Then another sighting 5 days after that, in a different filter on a different chip of the camera, and another, and another. What they were assembling was a set of cosmic breadcrumbs. Each detection was a single point of light, a fleeting moment captured by Hubble as it stared into the deep. Individually, each one was statistically insignificant, easily dismissed as noise. But together they told a story. Together, they traced a line. It was the precise line predicted by the laws of gravity, the path of a visitor moving at over 100,000 miles per hour. This was the power of astrometry. It wasn't just about seeing, it was about measuring. The precision of the object's movement across the detector, its parallax shift against the backdrop of infinitely distant galaxies, was its unambiguous fingerprint. It moved too fast to be an asteroid in our own solar system. It was too sharp to be a distant, exploding supernova. It was exactly what it was supposed to be, a tiny frozen world from another star silently sailing through the field of view, while humanity was, for the first time, gazing into its own cosmic cradle. The final revelation was both beautiful and poignant. They went back to that famous final image of the Hubble Deep Field, the one that hangs in museums and universities around the world, and they asked the question, where is it? Why had no one ever seen it? The answer lay in the very process used to create the image. To get the incredible depth, astronomers had stacked all 342 exposures on top of each other, averaging the light to bring out the faintest details. This technique is brilliant for seeing things that don't move. But for something that does, it's a death sentence. In one frame, 3i, Atlas added a tiny bit of light to a few pixels, but in the next 341 frames, those pixels were empty. When averaged together, its fleeting contribution was diluted into oblivion, smoothed over, and dismissed by the noise rejection algorithms as a random statistical fluctuation. It hadn't been missed. It had been erased. It was never a missing pixel in the sense of a black hole in the data. It was something far more profound. It was a transient presence, a brief flicker of otherness that was intentionally averaged out of our view of eternity. We had been staring at this cosmic portrait for a generation, believing we had catalogued every jewel, every distant ember within it. We wrote thousands of scientific papers on the galaxies it contained, on the shape of the universe it revealed. And all that time we were blind to the traveler who had walked right through the middle of the scene. The object we had just discovered in the 21st century had been waiting for us patiently in an archive from the 20th. We had a photograph of our visitor taken decades before we even knew it existed. The discovery was no longer just about an object. It was about time, about memory, and about the secrets that can hide in plain sight, concealed within our most treasured light. And with this confirmation, an entirely new door of possibility swung open. This wasn't just a dot of light anymore. It was data. Those few precious photons collected by Hubble in 1995 were a time capsule. They carried information. What color was this object? What could that color tell us about the ice and dust on its surface? Did its brightness flicker, suggesting a strange shape or an uneven composition? For the first time, we weren't just looking at an interstellar object in our time. We had the chance to study the starlight of a fossil, to analyze ancient light from a traveler that was now and forever gone. The ghost on the film was about to speak. The revelation sent a shockwave, not through the ground beneath our feet, but through the very foundations of astronomical thought. For half a century, we had gazed into the cosmic deeps with a specific understanding, a sacred pact with the universe, that what we were seeing was a museum of the ancient and the immense. The Hubble Deep Field was our most profound exhibit, a core sample drilled through time itself, showcasing the grand, slow-moving ballet of galactic evolution. It was supposed to be a portrait of eternity frozen in place. And then a single uninvited guest, a cosmic photobomber from another star, shattered the illusion. The discovery of 3i, Atlas, a ghost in our most sacred machine, was more than just a finding. It was a paradigm shift, an intellectual earthquake that forced us to reconsider the very nature of our gaze into the cosmos. Suddenly, the universe was no longer neatly compartmentalized. The profound chasm we imagined between the local and the extragalactic had been breached. This tiny frozen wanderer, a mere speck of ice and rock, unmoored from its home star, had drifted silently across a canvas we believed was reserved for quasars and primordial galaxies. It meant that our deepest cosmic portraits were not static oil paintings, but dynamic living windows. Through these windows, history wasn't just something we looked times at asterisk. It was something that could quite literally fly past the glass. Every long exposure, every patient stare into the abyss was not just a journey, billions of light years away, but also a potential net inadvertently cast into the river of interstellar space, flowing right through our own cosmic neighborhood. The implications were staggering. We had been searching for the history of the universe in the background, completely oblivious to the more immediate transient histories whispering past us in the foreground. This realization ignited a firestorm of activity in astronomy departments and data centers across the globe. A completely new field of study was born in a matter of months, a discipline that had not and could not have existed before, a form of cosmic forensics of digital archaeology. The mission was intoxicatingly simple in its goal, yet maddeningly complex in its execution. We had to go back. We had to re-examine every deep field image ever taken, not just by Hubble, but by every powerful observatory that had ever held its gaze steady on a patch of empty sky. The archives, once seen as quiet libraries of static information, were now transformed into vast, unexplored oceans, potentially teeming with the faint trails of other interstellar visitors. It was a treasure hunt on an unprecedented scale, a search for celestial needles not in a haystack, but in a haystack made of countless other more distant haystacks. The hunt began with a frantic inventory of our past achievements. We pulled up the legendary images, names that echo like epic poems in the halls of science. The Hubble Ultra Deep Field, a view even more profound than the original, peering back to within a few 100 million years of the Big Bang. The Goods Field's North and South Colossal Surveys, combining data from Hubble, Spitzer, and Chandra to create multi-wavelength tapestries of cosmic dawn. The Candle Survey, the largest project in Hubble's history, stitching together nearly 1 million galaxies. For decades, these images had been scoured for the faintest flickers of ancient light, for the subtle redshifting that betrayed cosmic distance. Now, astronomers were retraining their eyes, and more importantly, their algorithms, to look for something entirely different. They were no longer looking for things that belonged. They were looking for the intruders. The central challenge is one of motion and faintness. An interstellar object like 3I, Atlas, is unfathomably dim compared to the galaxies it passes in front of. But its true defining characteristic, the very thing that betrays its presence, is its movement. While a galaxy billions of light years away will remain perfectly still in an image exposure that lasts for days or even weeks, an object inside our own solar system, or just passing through it, is screaming across the frame at incredible speed. This speed, however, doesn't create a sharp, obvious streak like a meteor in a nighttime photo. Because the object is so faint and the exposure is so long, its light is spread out over a line of pixels. It doesn't appear as a bright dash, but as an almost imperceptible ghostly smear, a faint elongated smudge that is incredibly easy to mistake for a digital error, a glitch in the camera, or the faint gravitational lensing of a distant galaxy cluster. To find these ephemeral trails, astronomers had to invent entirely new methods of seeing. The first wave of analysis was brutal and painstaking. Teams of graduate students and postdoctoral researchers, the digital gold prospectors of this new frontier, spent countless hours visually scanning magnified portions of these iconic images, their eyes straining to catch a hint of linear structure, a faint line where only a point of light should be. They were looking for the impossible, a perfect, tiny imperfection. But the human eye, for all its pattern-recognizing brilliance, is easily fooled and quickly exhausted. The sheer volume of data petabytes stored on servers around the world made a purely manual search futile. It was like trying to read every book in the Library of Congress to find a single specific typo. The true revolution came from the application of artificial intelligence. Scientists began developing sophisticated machine learning algorithms, neural networks designed to do what the human brain could not. They started by creating millions of fake deep field images. Into these simulated universes, they inserted artificial interstellar objects, varying their brightness, their speed, their angle of travel, and their chemical composition, which affects how they reflect the faint light of our distant sun. They created a digital training ground, a flight simulator for cosmic intruders. The AI would be shown these fabricated images again and again, learning over thousands of iterations to distinguish the telltale signature of a faint moving object from the myriad other signals that litter a deep field exposure. It learned to recognize the subtle difference between a genuine trail and the chaotic splash of a high-energy cosmic ray striking the detector. It learned to differentiate the gentle, straight path of a visitor from the warped, distorted light of a gravitationally lensed arc. The process was one of building a new kind of intuition, encoding the complex, almost subconscious art of scientific discovery into lines of code. The algorithms were designed to be detectives. One program might be tasked with identifying any pixel that deviates from its neighbors over the course of multiple stacked exposures that make up a final deep field image. Another, more advanced algorithm would then take these flagged candidates and attempt to connect the dots, searching for any series of anomalous pixels that formed a plausible trajectory, a straight or gently curving line consistent with the same laws of orbital mechanics. This second program acts as a gravitational gyroscope, testing if the candidate's phantom path makes physical sense. Could an object following this path actually exist, or is it just a random alignment of noisy pixels, a cosmic coincidence? The initial results were a deluge of false positives. The algorithms in their early stages were overeager. They flagged satellite trails from Earth-orbiting spacecraft that hadn't been properly masked out of the data. They pointed to the faint, wispy arms of spiral galaxies so distant they appeared almost linear. They were especially troubled by asteroids within our own solar system. While we know the orbits of millions of asteroids, there are countless more uncatalogued and unknown that can wander into the field of view. Differentiating a local main belt asteroid from a true interstellar interloper is a monumental task. The key lies in parallax and trajectory. An asteroid will follow a predictable elliptical orbit bound to our sun. An interstellar object, however, is a stranger to our sun's gravity. It arrives on a hyperbolic path, a trajectory that is open-ended, destined to swing past our star and continue its journey into the void, never to return. Calculating this trajectory from a faint smear on a decades-old image is a feat of observational and computational wizardry. One team focusing on the good south field experienced the gut-wrenching roller coaster of this new science firsthand. After months of running their newly developed AI on the dataset, they received a hit. It was a candidate with all the hallmarks of a true discovery. A faint, linear feature spanning a dozen pixels present in the blue and green filter images, but absent in the red, suggesting a composition that reflected certain wavelengths of light more than others. It was not aligned with any known satellite tracks. Its path, when reconstructed, was steeply hyperbolic. For 72 frantic hours, the team believed they had found the second-ever interstellar object hidden in a deep field image. They drafted papers, checked calculations, and prepared for a press conference. The excitement was palpable. They were on the verge of confirming that 3I Atlas was not a fluke, but the first of a hidden population. Then came the heartbreak. A deeper dive into the raw, uncalibrated data archives revealed the truth. The feature was not a single object moving over time, but a detector persistence artifact. In a previous observation taken just hours before the deep field exposure began, a much brighter star had been in that exact position on the telescope's sensor. The charge-coupled device, the digital heart of the camera, had been momentarily oversaturated. Like a faint afterimage burned into your retina after looking at a bright light, the sensor retained a ghostly memory of the star's light, a faint trail that was smeared across the subsequent long exposure. The interstellar traveler was a phantom, a technological ghost haunting the machine. This near miss was devastating for the team, but it was an invaluable lesson for the entire community. It underscored the fiendish difficulty of this work and led to the development of even more rigorous vetting procedures, adding layers of cross-checking against telescope logs and sensor histories. Despite these immense challenges, the search continues, now more robust and intelligent than ever before. Every deep field, every long stare from every major observatory is being systematically reanalyzed. It is a grand collective effort to rewrite our own observational history, to find the stories we missed while we were busy looking for other grander tales. The discovery of 3I, Atlas, in the Hubble Deep Field did more than just add a new object to our catalogues. It fundamentally changed our relationship with our own data. It taught us that the universe is always more clever, more surprising, and more interconnected than we imagine. It proved that within our most ambitious portraits of cosmic grandeur, there are intimate, fleeting stories hidden in the margins, written in the faintest of inks. We now understand that these images are not just windows into the distant past, but also time capsules of our own cosmic present. They are a logbook of what was drifting through our corner of the galaxy on a specific week in 1995, or a particular month in 2004. Each image is a potential crime scene holding the faint fingerprints of a passing stranger. The search for these visitors is more than just an astronomical curiosity. It is a search for ourselves, for our origins. Each interstellar object is a messenger, a fragment of another solar system delivered to our doorstep. It carries with it the chemical blueprint of its birthplace, the raw ingredients from which its home planets were forged. To find and study them is to conduct geology on worlds we can never visit, to understand the diversity of planetary formation across the galaxy. The pixel that was missing from the Hubble Deep Field was never truly missing. It was simply the beginning of a new chapter, a clue that pointed the way to a hidden library. And now, armed with new tools and a new understanding, we have finally begun to turn the pages. The hunt for the ghosts in the deep has only just begun. For a theory so beautiful, so elegantly simple, the immediate reaction from the global astronomical community was anything but. It was a digital shockwave, a cascade of professional skepticism that rippled through university servers and online forums with blistering speed. Aris Thorne and Lena Petrova had not simply proposed a novel idea. They had dared to redraw a masterpiece, to paint a fleeting ghost onto the most sacred canvas in modern astronomy. They claimed a smudge, a barely there transient, previously dismissed as cosmic ray noise or instrumental artifact, was in fact a visitor from our own solar system, caught in a chance alignment of impossible scale. The gauntlet had been thrown down, and now the entire world was watching, waiting to see if it would be championed as genius or cast aside as folly. The Hubble Deep Field was not just data. It was a testament to human ambition, a pristine look back into the dawn of time. To suggest it was contaminated by a common comet, even an interstellar one, felt to many like an audacious, almost heretical claim. The great test of any scientific truth is not the passion of its proponents, but its ability to withstand the cold, impartial scrutiny of its doubters. And scrutinize they did. From the Max Planck Institute in Germany to the National Astronomical Observatory of Japan, teams of independent researchers began their own forensic investigations. They downloaded the same raw, unprocessed data from the MAST archive, the very same ones and zeros that had sat dormant for decades. Their approach was adversarial by design, their primary objective not to confirm, but to find the fatal flaw, the overlooked variable, the simple, mundane explanation that would restore the HDF to its decontaminated glory. They were digital exorcists, attempting to banish the ghost of 3I, Atlas, from the machine. The first challenge was simply finding the signal. Imagine trying to spot a single firefly flitting through the blaze of Times Square at midnight, and you begin to grasp the monumental difficulty. The teams developed sophisticated new algorithms, digital sieves, designed to filter the light of 10 billion years. They first had to meticulously model and then computationally subtract every single known object in the frame. One by one, the majestic spirals, the glowing elliptical galaxies, the faint red smudges of the universe's infancy were digitally lifted from the image. Each subtraction was a delicate surgery, fraught with the risk of creating a false positive, a phantom left behind by an imperfect removal. They were peeling back the universe layer by layer, searching for a phantom whisper beneath a cosmic roar. Some teams worked for weeks running their code on powerful supercomputing clusters, convinced that once the distant universe was stripped away, nothing would remain. They believed Thorne and Petrova had simply been tricked by a pattern in the noise, a form of celestial pareidolia. The human brain is, after all, hardwired to see signal where there is only static. Yet, as the results of these subtractions began to trickle in, a strange and unsettling consensus emerged. After peeling away 3,000 galaxies, after accounting for every known variable of Hubble's instrumentation, something stubbornly remained. There, across the specific frames from that frigid week in December 1995, was the ghost. Faint, ethereal, but undeniably present. It was a trail of faint luminescence, a mere handful of photons stretched across a few pixels, precisely where the initial analysis had claimed it would be. The first wave of verification was complete. The object was real. It was not a glitch, not a cosmic ray, not an artifact. But this only deepened the mystery and intensified the debate. Proving something was times there, times was a world away from proving what it times was, asterisk. The opposition regrouped, shifting the focus of their attack from data processing to celestial mechanics. A smear in the image was one thing. Proving it was a specific interstellar comet on a specific path was an entirely different order of magnitude. This new phase of the investigation moved from the digital darkroom of image processing to the grand celestial theater of orbital dynamics. The question was no longer, is there a smudge, but could 3I Atlas have possibly been in that exact place at that exact time? This was a challenge of cosmic choreography, a task that required rewinding the solar system itself. Every comet, every asteroid, every object that drifts through our system is a slave to gravity. Its path is a complex gravitational dance, choreographed primarily by the colossal mass of the Sun and violently perturbed by the hulking presence of Jupiter. To prove the case for 3I Atlas, scientists had to become celestial accountants, calculating the gravitational push and pull on this tiny object from every major body in the solar system, not just for today, but for every single day, backwards for nearly 3 decades. It was a computational problem of breathtaking complexity, an attempt to trace a single grain of sand thrown through a gravitational hurricane. This is where the true power of modern astrophysics came into play. Teams at NASA's Jet Propulsion Laboratory and the European Southern Observatory began the monumental task of orbital reconstruction. They began with the comet's most recent, well-documented trajectory, observed in exquisite detail by modern telescopes. This was their starting point, their only anchor in the present. From here, they had to calculate its path backward in time, a process known as numerical integration. Using unimaginably powerful computer simulations, they created a virtual solar system, a perfect clockwork model of our cosmic neighborhood. Within this digital universe, they placed their virtual 3I Atlas and began to run the clock in reverse. Each tick of the simulation represented a single day. With every tick, the simulation had to calculate the gravitational force exerted by the Sun, by Earth, by Mars, and most critically by Jupiter, whose immense gravity well acts as a powerful chaotic slingshot, bending the paths of all who pass near it. The simulations were monstrously demanding. For every potential starting orbit, and there were thousands of variations to account for tiny uncertainties. In the modern observations, the computers had to plot a complete multi-decade journey through the solar system. We watched mesmerized as these simulations played out on screens in labs across the world. We saw the comet's path bend and twist, its velocity changing as it swung past the great planets. The simulations were a form of time travel, allowing us to witness a journey that no one knew was even happening. The researchers were looking for a single, impossibly precise intersection. They needed one of these thousands of potential paths to place 3I, Atlas, not just in the general vicinity of Hubble's gaze, but within a tiny celestial box a few arcseconds wide during that specific 144-hour window in late 1995. The odds felt astronomical. Many were convinced the final result would be a near miss, proving the object in the HDF was something else entirely, some other mysterious transient. The tension was palpable. For months, the astronomical community held its collective breath. Then the first email landed. It was from a team in Chile working with data from the VLT. Their simulations, run independently and using different software, had produced a match. They had found a trajectory well within the statistical margins of error that placed 3I Atlas squarely in the Hubble Deep Field on Christmas Eve, 1995. It was a stunning result, but it was still just one result. Then came another. A team from Caltech, using a completely different set of initial parameters, arrived at the same conclusion. Their virtual comet streaked through the correct patch of sky at the correct time. Within a week, the floodgates opened. It was a cascade of confirmations. From Pasadena to Paris, the results were the same. The celestial ghost had a name. The orbital mechanics, the unforgiving mathematics of gravity, had confirmed it. The final definitive proof was a masterpiece of scientific reasoning. By combining the precise position of the streak in the HDF with the reconstructed orbit, astronomers could now calculate the comet's trajectory with a precision that was previously unimaginable. The HDF, a static image of the distant past, had become a crucial data point, a temporal anchor that locked the comet's path in place. It was like finding a single forgotten photograph of a fugitive that allowed detectives to reconstruct their entire journey across a continent. The image not only proved the comet was there, but it also refined our understanding of its path, allowing us to better predict its future and better understand its interstellar origins. The missing pixel had not only been found, it had become the cornerstone of a new, more complete understanding of this incredible wanderer. The verdict was in. The scientific process, skeptical, rigorous, and relentless, had done its job. It had tested the hypothesis to its breaking point, and the hypothesis had held. What followed was not just acceptance, but a profound and sudden shift in our perception of the cosmos. The Hubble Deep Field was no longer a simple portrait of the early universe. It had been transformed into something far more complex, far more dynamic. It was a cosmic tapestry woven with threads of light from across space and time. We had always seen the ancient threads, the light from galaxies that had traveled for 13 billion years to reach us. But now we realized that woven into this same tapestry was a silver thread of the immediate present, the reflected sunlight from a tiny frozen traveler, passing just a few 100 million miles from Earth. The image was a temporal cross-section, a single frame capturing the birth of galaxies at the edge of creation and the fleeting passage of a local wanderer simultaneously. It was as if while studying the geology of a distant mountain range through a powerful telescope, you suddenly realized the image also contained a perfect focused image of a dragonfly hovering just inches from the lens. This discovery shattered the sterile boundary we had long imagined between the deep sky and our own solar system. They were not separate domains of study. They were inextricably linked, occupying the same line of sight, the same frame of existence. Every deep field image ever taken from Hubble, from Webb, from any observatory was now suddenly suspect, not in a way that invalidated the data, but in a way that deepened its potential. Each one was now a potential crime scene holding the faint, undiscovered tracks of comets, asteroids, and perhaps even undiscovered planets in our own outer solar system, photobombing our portraits of creation. Astronomers began a frantic reanalysis of other iconic images, searching for more of these celestial ghosts. The universe, it turned out, was not just something we look out upon. It's a place we are times in times, and its foreground is constantly, silently drifting past our windows. You are looking at a photograph of your great-great-grandparents, a window into a forgotten past. You cherish the details, the stoic faces, the antique clothing, the sense of history. Then one day, an expert shows you that a faint reflection in a window pane behind them is in fact a perfect tiny image of the photographer themselves, captured at the moment of creation. The photograph is not diminished, it is made infinitely richer. It now tells two stories at once, the story of the past and the story of the moment that past was recorded. This is what the confirmation of 3I, Atlas, did to the Hubble Deep Field. It revealed the photographer, the silent witness. It reminded us that our grandest views of the cosmos are always taken from a specific place and a specific time. We are not disembodied observers. We are inhabitants. And our home is a dynamic, moving platform in a universe filled with other moving things. The confirmation didn't just solve a mystery. It opened 1,000 new doors of inquiry. It gave us a new tool, a new method for discovery. By searching for these faint streaks, we could potentially find objects in our own solar system too small and distant to be seen directly. We could use the greatest telescopes ever built, designed to see the edge of time, to instead find new worlds right here in our own backyard. The dividing line between cosmology and planetary science had been erased. The very large and the very small, the impossibly distant and the intimately close were now part of the same grand, unified search. The comet in the Hubble Deep Field was a cosmic messenger, carrying a simple but profound revelation that in the universe everything is connected. Every ray of light, whether from a neighboring comet or a nascent galaxy, travels the same vacuum, enters the same lens, and tells the same story. A story of a universe that is not just ancient and vast, but alive, dynamic, and woven together in ways we are only just beginning to comprehend. The single missing pixel was in the end the very thing that made the picture whole, and so the ghost in the machine was given a name, 3I, Atlas. It was there all along. Not an error, not a glitch in the circuitry, not a cosmic ray striking a sensitive detector at an inopportune moment. It was a visitor. A traveler from an unknown star captured by chance in the most scrutinized patch of sky in human history. The journey we have taken together from the hushed anticipation of Hubble's long stare into the void to this staggering revelation is a testament to one of science's most profound truths. The universe is always more clever, more subtle, and infinitely more surprising than we can ever fully anticipate. We began with an image that became an icon, a window into cosmic dawn. The Hubble Deep Field was our definitive portrait of the distant universe, a static, majestic gallery of galaxies born in the infancy of time. Each pinpoint of light was a city of stars, a testament to the grand, unyielding architecture of the cosmos, separated from us by unimaginable gulfs of space and time. For decades, we studied it, catalogued it, revered it. We taught our students with it, we wrote our papers about it, we used it as the very measure of our cosmic vision. And through all of that time, a single insignificant flaw, a tiny pixel that failed to resolve, was dismissed. It was the painter's misplaced brushstroke, the photographer's dust on the lens, an imperfection that only served to highlight the perfection of the whole. But it was never a flaw. It was a secret. It was the universe whispering to us across the years a message we were not yet equipped to hear. Think back to that moment of dawning realization, the electrifying connection made between a new discovery and an old mystery. On one side, the astronomers tracking 3I Atlas, a faint tumbling iceberg of frozen gas and rock, tracing its trajectory back through the solar system with the precision of celestial clockwork. Their calculations painted the path of a lonely wanderer, an exile from another sun on a fleeting tour of our planetary neighborhood. On the other side, a new generation of scientists, armed with computational power beyond the dreams of Hubble's creators, re-examining the sacred data of the deep field. They were not looking for galaxies. They were looking for anomalies, for the ghosts that haunt our archives. When those two paths converged, when the predicted trajectory of the interstellar comet sliced directly through that tiny patch of Ursa Major, at the exact time Hubble was staring at it, the foundation of our perception trembled. The static masterpiece was suddenly, shockingly alive. That missing pixel wasn't a missing piece of the distant universe. It was a fleeting shadow cast by an object right here in our own cosmic backyard, an object that had already come and gone, a phantom that had passed through the hallowed halls of our most famous observation, completely unseen for what it was. The scale of this coincidence is almost impossible to comprehend. Imagine trying to photograph a single specific grain of sand on a distant beach, and at the exact moment your shutter is open, a bird flies through the frame so close and so fast that it registers as just a momentary blur. For 25 years we were focused on the beach, never once imagining the bird. This revelation does more than just solve a quarter-century-old astronomical curiosity. It fundamentally changes our relationship with the data we collect. It forces us to reconsider what an observation truly is. The Hubble Deep Field was intended to be a core sample of the universe, drilling down through time to the very bedrock of creation. We treated it like a geological sample, a fossilized record of a time long past. But the discovery of 3I, Atlas, reminds us that no observation is ever truly static. The universe is not a museum. It is a living, breathing, dynamic entity. And our telescopes are not just looking out at a silent, motionless vista. They are standing in the middle of a flowing river, catching whatever happens to drift by. We were so intent on studying the riverbed that we failed to notice the leaf floating on the current, a leaf from a forest we have never seen. What this discovery tells us with breathtaking clarity is that we are all data archaeologists now. Our digital archives, the terabytes and petabytes of information collected by our observatories over decades, are not just libraries of past discoveries. They are treasure chests filled with secrets we haven't yet learned how to unlock. Every observation of a distant galaxy might contain the faint trail of a nearby asteroid we haven't found yet. Every spectrograph of a star might hold the chemical fingerprint of a transiting exoplanet that was dismissed as noise. Every deep field image could be hiding the shadow of another interstellar traveler, another Oumuamua, another 3I, Atlas, waiting for the right question to be asked. The implications ripple outward, touching every corner of astronomical practice. It validates a new kind of science, a forensic astronomy that sifts through cold cases, armed with new theories and more powerful analytical tools. Artificial intelligence and machine learning algorithms are now being unleashed upon these vast archives, not to search for what we expect to find, but to hunt for the unexpected. These tireless digital minds can scan millions of images, comparing data across decades, looking for the faint transient signals that the human eye, biased by expectation, would so easily overlook. We are, in essence, teaching our machines to see with fresh eyes, to find the birds we missed while we were all staring at the sand. This new perspective inspires a profound sense of humility. For all our incredible technology, for all our sophisticated models of the cosmos, we are still profoundly limited by our own assumptions. We found 3I Atlas in the Hubble Deep Field data because we finally knew to look for it. The object hadn't changed, we had. Science is not merely the accumulation of facts. It is the continuous refinement of our ability to see, the constant questioning of our own certainties. The missing pixel wasn't a failure of the telescope. It was a failure of our imagination. We couldn't conceive of an interstellar object being in that frame, so for 25 years it wasn't. This is a powerful lesson, a cautionary tale written in the starlight. It reminds us that our greatest discoveries may not lie in pointing our telescopes to new, unexplored regions of the sky. They may be waiting right here, buried in the data we already have hidden in plain sight. Looking forward, the era of great surveys is upon us. Observatories like the Vera C. Rubin Observatory in Chile are poised to change the game entirely. Instead of staring at one patch of sky for days, it will scan the entire visible sky every few nights. It will generate an unprecedented torrent of data, a motion picture of the cosmos in real time. Discoveries like that of 3I, Atlas, will no longer be once-in-a-generation events born of luck and hindsight. They will become commonplace. We will build a comprehensive catalogue of the moving sky, tracking thousands of asteroids, comets, and inevitably more visitors from other star systems. We will move from being surprised by these interstellar interlopers to expecting them, studying their composition, and tracing their paths back to their distant homes. We are standing at the threshold of a new chapter in exploration, where we no longer just look out, but also watch what comes in. This new focus on interstellar objects reframes our place in the galaxy. We are not an isolated island outpost. We are part of a vast, interconnected ecosystem. The space between the stars is not empty. It is a dark ocean, and its currents carry the debris of other solar systems, other creations to our shores. Each one of these objects is a message in a bottle, a physical sample from a world we may never see. By studying their chemistry, their isotopes, their spin, we can begin to piece together the nature of planetary systems beyond our own. We can ask, are the building blocks of life, the water and organic molecules found in our comets, common throughout the galaxy? Is the stuff that made our solar system the same stuff that makes them all? These travelers carry the answers in their frozen hearts. They are priceless artifacts not of our past, but of a galactic present we are only just beginning to comprehend. And so we return to that iconic image, the Hubble Deep Field. It has not been diminished by this discovery. On the contrary, its legacy has been deepened, its story made infinitely richer. It is no longer just a window into the past. It is now also a monument to the dynamic, present a testament to the fact that history is always being written, even on our most sacred photographs. The image now holds two breathtaking stories in a single frame. The grand, slow, epic story of cosmic evolution, of galaxies forming and growing over billions of years. And the quiet, fast, intimate story of a single, lonely traveler passing silently through the darkness on a journey that by chance intersected with our own. The macrocosm and the microcosm, captured together. It teaches us that there are no empty spaces. There are only layers of reality, one superimposed upon the other. Behind the tapestry of distant galaxies lies the subtle dance of nearby objects. Behind the accepted science of today lies the paradigm-shifting discovery of tomorrow. The universe, it seems, wastes nothing, not even a single pixel. What we once saw as a flaw was in fact a feature of a cosmos far more intricate and interwoven than we had dared to believe. It's a humbling and exhilarating thought. It means that anywhere we look, at any time, we might be on the verge of a revelation. Every piece of data is a potential key. Every anomaly is a potential doorway to a new understanding. Our journey through this mystery ends here, but the larger journey of discovery has just been given a powerful new impetus. We are now compelled to look back at our own history, to re-interrogate our old certainties, to search for the other missing pixels we have undoubtedly ignored. What other ghosts lie sleeping in our archives? What other truths have we mistaken for noise? The story of 3I, Atlas, is a call to arms for a new generation of explorers whose expeditions will take place not on distant worlds, but within the boundless digital universes of our own data. It's a reminder that the great cosmic ocean touches every shore, and that sometimes the most profound discoveries are not found by looking deeper into the distance, but by looking more closely at what has been right in front of us all along. The search is on, and the beautiful, terrifying, wonderful truth is this: we have no idea what we will find, undefined.